Alright, hello everyone. The notes are wrong here. We're not doing the integral test today. We're going to wait till next chapter to do that. But today we're going to talk about partial fractions and telescoping series. So up until this point, if you were given a series, put it in a generic set here, and asked, does this converge or diverge? The first thing you should look for is it geometric? If it's geometric and r is between -1 and 1, then you could say yes. Right? If it's geometric and r is absolute value of r is greater than or equal to 1, then you could say no. Right? So geometric is your first go-to. Second thing you should do is take the limit as n goes to infinity of said sequence. Right? Just the sequence. And if it's not equal to 0, you could say, nope, divergent. So divergent. If it's equal to 0, you could say, maybe. Maybe. All right? And then from there, the only test we've got so far at our fingertips is the ratio test. Right? So the ratio test says take the limit as n goes to infinity of a sub n plus 1 over a sub n. If that value is less than 1, then we can say yes, converges. If it's equal to 1, it's inconclusive. And if it's greater than 1, we could say divergent. So we could say convergent at this point. We could say convergent if and only if ratio test yields a value less than 1, or it's geometric with an r value between -1 and 1, right? Or the absolute value of r is less than 1. All right, so that's how far we've come so far today. Today we're actually going to talk about the only other test that we'll test all year where we can calculate the actual infinite sum. So geometric, we can go a over 1 minus r. Today we're going to talk about using partial fractions to determine if you have a telescoping series, which is a potential to find the actual. Not just say it's convergent, but find the actual sum. All right, let's get started. Okay, so rewriting terms, telescoping series come in this form, right? Where it'll be a over something, kind of like this. All right, so I've got 1 over n times n plus 1. Well, I have to use some algebra, right, to come up with what a and what b would equal. All right, but if I can get it in this form, potentially I can get what's called a collapsing sum, and I might get a finite sum there. Okay, so we're going to go ahead and jump into an example and then look at one of the homework problems as well. All right, so here I have this infinite series. This series looks to be, let's just write out the first couple terms. That'd be 1 over 2 plus 1 over, what would that be? 1 over 6 plus 1 over, that'd be 3 times 4, which would be 12. I would say, well, obviously it's got a chance, right? Because the limit as n goes to infinity of this thing, 1 over n times n plus 1, right, will equal 0. So it has a chance. What I want to do is I want to express this in partial fractions. So I'm going to skip part A. We could use the ratio test to show that the ratio, I think the limit in that case as n goes to infinity of a sub n plus 1 over a sub n also comes out to be 0. So we know it's convergent. Okay, you can do the algebra on that on your own. What I want to do is jump into the partial fraction piece. So I want to write 1 over n times n plus 1 in the form a over n plus b over n plus 1. Alright, so the first thing that you want to do is you want to get rid of the denominator. So I would multiply by everything you see in the denominator. I'd multiply by n times n plus 1 everywhere. Well, in our first term, this would just become a 1. A over n would become a times n plus 1. B over n plus 1 would become b times n. Okay, now I'm going to throw this in here over on this side. That was a poor choice in colors. I guess I'll just do this, I don't care. Just trying to get fancy. Okay, and I'm going to do this using two methods. Here's method number 1. Method number 1 takes a little bit more algebra, but it's how I've set up my key, and it's what it is. Okay, I'm going to expand the right side and write an, that should be an n, plus a plus bn. Okay, now I'm going to write this in red, 0n plus 1. I'm writing that in blue for a reason, you'll see in a second. Then I'm going to combine my two that have an n combined here. I'm going to call that a plus b n. And this a is all alone. So now I can lock these in and set them equal. Right? A plus b then equals 0. That means a equals negative b. Okay, and what does a equal? A equals 1. Therefore, if a equals 1, then b equals negative 1. Okay, so if a equals 1 and b equals negative 1, then 1 over n times n plus 1, its sum from n equals 1 to infinity would be equivalent to the sum from n equals 1 to infinity of a over n plus b over n plus 1. So I've taken that right here, I've taken this first sum and I've put it into this form. Perfect. Okay, I want to go back and do this using method 2 now. Method 2 is going to be a lot quicker. Okay, where do I want to be? I want to be... Let's go right here. So here's method 2. You don't have to use all the algebra. Alright, come on now. I have to do this live, otherwise if I pause it and try to erase it, it like acts weird. Okay, so here's your other option. Option 2. What if n equaled 0? Well, if n equaled 0, I put a 0 in for n everywhere I see it. If n equaled 0, then it looks like I'd get 1 equals a times 1 plus 0. So it looks like a would equal 1. Boom. Nice. Too easy. Okay, so let me hold that in my back pocket over here. A equals 1. Actually, I need to go back. So just remember a equals 1. We already knew that anyways. What if n equaled negative 1? Why would I pick negative 1? Because negative 1 will negate that. So if n equals negative 1, what do I get? I still get 1 equals, that would be a times 0 plus b times negative 1. So that means 1 equals negative b, so b equals negative 1. So in essence, what did I do for part 2, or option 2 of our algebra? I picked values for n that would make this 0, so I set this equal to 0. So I plug in that, and I plug in that. And that will get me my values for a and b much quicker. So I've got here a, and I've got here b. Okay, so now what, right? That's part 1 complete. Hence, find the sum of the above infinite series. Okay, so this is partial fraction decomposition from here to here. That's partial fraction decomposition. I'm terrible at spelling. Okay, that's partial fraction decomposition. Here is the telescoping piece. I'm going to write out the first 4 terms of this sequence or series right here. First 4 terms. Term 1. When n equals 1, what do I get? I get 1 over 1. So I get 1 minus 1/2. Okay, there's term 1. Term 2. When n equals 2, I get 1/2 minus 1/3. Okay, term 3. I would typically go out at least 4 terms, maybe even 5. We'll just think term 3. I got caught up in my own thinking. That'd be 1/3 minus 1/4. Term 4. That'd be 1/4 minus 1/5. This is an infinite series, therefore it will go on forever. I'm going to add all these terms up, and you're going to see something sweet. We get a cancellation. This is the telescoping piece, right? It's folding up on itself. This is also called, in some areas of math, the collapsing sum, right? So what do each of those equal? Well, that'd be 0, that'd be 0, that'd be 0, that'd be 0, on forever. What's the only thing that's left? 1. So that means that this sum right here equals 1. Okay, that is partial fraction decomposition with the telescoping series. I'm going to try to draw a telescope. That's decent, right? And that's, I don't know, what is that, a cannon? All right, let's go to a homework problem. All right, real quick now. We're going to write this as a over something plus b over something. So how would I come up with those somethings? Well, I'd factor this. So that'd be n plus 2, n plus 1. So that'd be a over n plus 2 plus b over n plus 1. I'm going to use method 2 now. Use method 2. So method 2, I set equal 2 n plus 3 over n plus 2 n plus 1 equal to a over n plus 2 plus b over n plus 1, and I'm going to multiply everything by n plus 2, n plus 1. Okay, so my first term would become 2n plus 3. Here I would get a times n plus 1 plus b times n plus 2. Alright, so if n equaled negative 1, okay, if n equaled negative 1, check out what I get. 2 times negative 1 plus 3 is equal to, a will disappear, right? But I'd get b times 1. So b equals 1. Okay, what if n equaled negative 2? Well, if n equaled negative 2, I'd get a negative 1, excuse me, I'd get a negative 4 plus 3, I was thinking ahead. That'd be a times negative 1. So then negative a would equal negative 1, so a would equal 1. So if I were to write this out, 2n plus 3 over n times over n plus 2 times n plus 1 would be the same as 1 over n plus 2, that's a, plus 1 over n plus 1. So I can tell you right now that this will not collapse. And the reason why is as I look at this here, I'll put it in green. As I look at this here, all terms are going to be positive. So there's no way it's going to collapse. So my partial fraction decomposition did this for me. It got me here. Right? But I know because that both those values, A and B, are positive, and even if both values are negative, so if they're both the same sign, it's definitely not going to converge. So I know that this series, right, this series from n equals 1 to infinity of 2n plus 3 over n plus 2, n plus 1, I know that's going to be divergent. Okay, folks, that's it for today on partial fraction decomposition and the telescoping series. Have a great day and see ya next time.